The 21st century started off with a bang as volcanoes erupted all over the world. Iceland, the Canary Islands, southern Japan, and off the coast of Tonga, blasted by the most powerful eruption of the century so far. While these volcanoes can cause death and mayhem, they pale in comparison to the supervolcanoes that some believe drove some of the Earth's mass extinctions and could happen again.
The worst possible consequences of a super eruption would be an existential threat to human beings.
We are nothing in comparison to that.
One of the most powerful supervolcanoes on Earth sleeps in the very heart of the United States, in Yellowstone National Park. Its origin dates back some 2 billion years. So far, it has detonated 3 super eruptions around 700,000 years apart, and it's about due for the next one.
Yellowstone is definitely a big system. It is really massive. The caldera is huge. It's tens of kilometers across, but also in terms of its depth.
The Yellowstone supervolcano churns with the largest reservoir of magma on Earth. That has scientists concerned. Its seismic and geothermal activity have been rumbling for the last 10 years. Does that mean the giant is beginning to stir? If Yellowstone does erupt, what would happen? The answer is indisputable and inconceivable. If the supervolcano exploded today, it would destroy a huge part of North America and disrupt life on Earth for centuries.
Chaos. It would be a major ecological and human disaster.
What would the end of the world as we know it look like? Pyroclastic flows, breaking at hundreds of kilometers per hour, annihilating everything in their path. Huge amounts of ash, smothering thousands of square kilometers across the North American continent. And then, magmatic gases, triggering volcanic winter around the world for decades to come.
Basically, there's no escape.
There's no way of preventing it. You just gotta kind of prepare for it.
Preparation is easier said than done. Yellowstone is the most powerful and potentially the most dangerous supervolcano on Earth. An eruption would be 1,000,000 times more cataclysmic than the bombing of Hiroshima. Would humanity survive it? Would we even want to? After the apocalypse, what kind of world would be left? Volcanologists agree. The question is not whether the Yellowstone volcano will awaken, but when. It is one of the most beautiful and best preserved natural sites in the world, but potentially one of the most dangerous. Yellowstone National Park. Straddling the states of Wyoming, Idaho, and Montana, its sumptuous landscape covers more than 1,000,000 hectares, over an area 88 kilometers long and 95 kilometers wide.
There are lots of special places on Earth, and Yellowstone, I think, is one of those.
It hasn't been altered as strongly as most areas of the world.
It's wonderland on its own. It's almost impossible to believe.
Yellowstone National Park is the oldest national park in the world and the most visited in the United States. After being discovered by a member of the famous Lewis and Clark expedition in 1806, President Grant signed a protection order in 1872. It was listed as a UNESCO World Heritage Site in 1979. Here, the wildlife roams freely across more than 9,000 square kilometers of vast plains amid picture postcard landscapes located at an average of 2,400 meters above sea level. It is home to more than half of the world's geothermal phenomena, producing energy below the surface of the Earth. For many millennia before becoming a park, this vast territory was already inhabited by Native Americans. The Nez Perce, or Blackfeet tribes, gathered around geysers and collected obsidian stones from ancient lava flows. Being very much in touch with nature, they could sense the stirrings in the depths of Yellowstone.
It was known to be a volcanic system because even some of the early explorers had learned from some of the indigenous peoples of the area that there was perhaps a volcano somewhere up near the headwaters of the Yellowstone River.
They recognized that there were a lot of volcanic deposits in the area, so they kind of had an inkling of it was a large volcanic system.
While the Native Americans were aware of living in a sometimes hostile natural environment, Yellowstone Park was initially not regarded as an area of interest to geologists, but a tragic event awakened the attention of scientists around the world. It all began with a deadly earthquake in the late 1950s.
There was a magnitude 7.3 earthquake. We call that the Hebgen Lake earthquake. And that happened just west of the park, just outside of the park.
That's the largest earthquake that has ever been recorded in the Intermountain West of the United States.
The biggest effects, of course, were out where the earthquake occurred, out by Hebgen Lake, where you had a lot of damaged roads, where roads were blocked, people were trapped. Then it caused a big landslide to occur. And that landslide came down on a campground and buried 28 people.
It killed a large number of people. It dammed a river and created a brand new lake. That created all kinds of damage in Yellowstone National Park as well, damage to roads with landslides. And the shaking from that event caused a large number of new geysers to form and existing geysers to change their behavior.
The following day in the park, just a few kilometers away, to the astonishment of all, 289 hot springs exploded into the sky in the form of geysers. Later, cracks in the ground appeared, releasing plumes of toxic gases. There could be no doubt that the earthquake at Lake Hebgen had triggered a great deal of underground activity in Yellowstone. And yet the area is not located on the edge of a tectonic plate. What exactly was going on in the heart of the United States?
There were a lot of seismometers that were put in the area, a lot of research that was done into earthquake activity, and it was found that Yellowstone is actually one of the most seismically active areas in the United States.
These earthquakes were of volcanic origin, triggered by an accumulation of underground magma. Scientists also discovered that the region is active because it is located on a hotline. It is a thermal anomaly. Starting some 2,900 kilometers below the surface, a hot spot brings up fragments of magma, producing the volcanic and seismic activity seen at ground level.
And you can imagine this as a bit of a torch that is fixed. The North American continent is moving, is drifting toward the west.
And so you'll get little volcanoes, the blowtorch pops through every now and then, and you'll get a chain of these volcanoes.
Volcanoes kind of pimple upward along the Snake River Plain in southern Idaho. If you go to the most western side of Idaho, you get to the oldest volcanism, and then it gets younger and younger as you progress up towards Yellowstone today.
The 3 million plus tourists who come here every year are blissfully unaware that they are walking across a ticking time bomb of unimaginable power. Visitors are oblivious to the secret that lurks beneath Yellowstone Park, the invisible volcano that may one day erupt, and in doing so, profoundly disrupt human activity.
We have to bear in mind that what we call supervolcanoes can also produce small eruptions.
Yellowstone is an example. Most of the eruptions are actually very small, and there were 3 large eruptions.
Yellowstone has experienced 3 major volcanic eruptions. The oldest and most powerful occurred some 2.1 million years ago at Huckleberry Ridge. It would have covered Texas with 4.5 meters of volcanic ash. The second, 1.3 million years ago, was at Mesa Falls. Finally came the third eruption at Lava Creek, some 640,000 years ago. These events produced astonishing quantities of magma, up to 2,450 cubic kilometers in each case. These extraordinary magma flows and the violence of the explosions make Yellowstone a supervolcano.
A supervolcano is really a volcano which has been able to produce an unusually large eruption. Unusually large in this case means several hundred, maybe 1,000 times larger than a common eruption that we've seen in historical time.
The VI, Volcanic Explosivity Index, is a scale that volcanologists use to measure the explosiveness of an eruption. So a super eruption has a VI 8.
On a planetary scale, these eruptions have a huge impact on the ecosystem and on humanity.
The number of supervolcanoes can be counted on the fingers of one hand. Over the past 2 million years, there have been about 15 super eruptions worldwide. Today, most of these supervolcanoes are dormant. But for how long? The Yellowstone supervolcano was formed during its last super eruption. Its collapse created the current caldera, a crater which today extends over 65 kilometers, or 1/3 of the national park.
A caldera is a large depression that has formed because of the collapse of a magma chamber.
Yellowstone Park is actually in the caldera. This caldera is so huge that it cannot be seen in the landscape.
The calderas can be so large that you can build entire towns and cities inside them.
They can have diameters between 1 and 100 kilometers.
It's not recognized that you're actually inside a volcano. This is why trying to raise awareness of what a supervolcano is, or a large caldera is, it can be very difficult because they don't look like a stereotypical volcano that you would see in, say, a film from Hollywood.
At first sight, the uniform nature of the landscape offers few clues. So what does an exploding caldera look like? And what exactly happened? The series of events leading to a supervolcano eruption is always the same. Several kilometers below the Earth, the magma chamber begins to liquefy under the effect of very high heat. The magma then fragments and rises a few dozen meters toward the surface. The pressure from the chamber eventually weakens the Earth crust, splitting it open. The immense pressure and very high temperatures produce an explosion, causing the volcano to collapse in on itself, giving rise to a 4,000 square kilometer caldera.
And when that magma chamber emptied, the surface fell into the space that was created, the space that was vacated by all of that magma that erupted, and that left this structure that we call a caldera.
Kind of like a piston cylinder plummeting down into a liquid, which then pushes more material outward and makes this very flat surface.
The area of the caldera gives us some idea of the surface occupied by the magma reservoir that is at the base of this volcanic system.
A lot of that hole that was created by the big explosion has been filled by lava flows and by glacial debris and by lake sediment. It's not necessarily clear you're looking at a volcanic area unless you know the features that you're looking at.
After each supereruption, the magma chambers fill up again, and the Yellowstone caldera now has the largest amount of magma of any in the world. For scientists, the threat is ongoing and a constant worry. But volcanologists have another cause for concern. If we take the dates of the past 3 supereruptions, the calculation is simple. The park's dormant volcanic system seems to wake up every 700,000 years or so. Given that the last supereruption took place 640,000 years ago, another is due. Scientists now anticipate another major eruption, but the question is, when? And what will be its magnitude?
Yellowstone's 3 previous super-eruptions are huge indications of what might happen in the case of a 4th. We know the volume, we know the surface areas, we know the quantities.
The signs are clearly visible in the heart of the caldera. The impressive forest of dead trees testifies to the presence of sulfur in the soil and in the streams. Scientists at the Yellowstone Volcano Observatory closely monitor the caldera. The slightest variation or change in physiognomy is a warning sign of a potential eruption.
As that pressure increases, it causes the ground to move. Now, the movement may be just a few centimeters, but we can detect that with satellite measurements, global GPS measurements, but also from traditional surveying technique.
In the 1970s, while hiking through the park, a seismologist noticed that the landscape had changed. On the south shore of the lake, the bases of tree trunks had become submerged in water. The only explanation was that the opposite bank had risen and the slope had changed.
Between the 1920s and the 1970s, it was seen that the land actually rose in Yellowstone caldera by over 70 centimeters. And Yellowstone sort of goes up and down all the time on its own, typically at a rate of 2 to 3 centimeters a year or so. Now, before an eruption, we might expect to see very dramatic uplift.
When the magma rises, when an eruption is imminent, tiny earthquakes occur. Micro-earthquakes have a magnitude of only 1 or 2, which is very weak. They barely register, but there are hundreds or even thousands of them every day.
Is the local, very localized breaking of rock as pressure builds up underneath the volcano.
The classic sign of an imminent eruption is a combination of swelling and microseismicity. If we have between 100 and 1,000 micro-earthquakes per day, allied to swelling of just a few millimeters or a few centimeters, the signs are worrying. The magma is moving and swelling. The situation then becomes critical.
We record on average about 1,500 to 2,500 earthquakes a year, so it's a very seismically active area. They don't always happen on a regular basis either. We get what we call swarms of earthquakes. For example, there's kind of an east-west band of seismicity between the Hedgen Lake area and North Geyser Basin, where we see most of the earthquakes in Yellowstone.
The Norris Geyser Basin is the park's most dynamic geothermal area. This is the visible part of 115,000 years of seismic activity. It is the oldest and the hottest spot, with temperatures hitting 237 degrees Celsius in some springs. The water here is acidic, and in this post-apocalyptic landscape, you get a sense of the volcano breathing, swelling, and purging itself of the pressure just below the surface.
There's always kind of weird things going on there that we're learning how hydrothermal systems work.
Sometimes I like to think of geyser plumbing systems as like the plumbing in an old house. You know, maybe the plumbing is sort of rotting away. The plumbing is very tight because of all the minerals that have precipitated around the plumbing on the inside of the pipes. And if you shake that, pipes are going to break here and there, and things just aren't going to work very well, right? That's sort of what Yellowstone is like. And so when you have these large earthquakes shaking the plumbing system, it's going to break, and you'll see geysers doing all kinds of weird things. So that's really the hazard that I think will impact this area on a human timescale.
Scientists are acutely aware of the threat posed by the Yellowstone supervolcano. Since the installation of seismographs in the caldera, volcanologists have been scrutinizing seismic disturbances, and their intensity has increased sharply since the turn of the century. Correct interpretation of these seismic phenomena makes it possible to better predict eruptions and thus save precious time in evacuating the area. Everyone remembers what happened at Mount St. Helens. After several weeks of seismic disturbances, fractures, and deformation, on May 18, 1980, at 8:32 a.m., the volcano erupted. It was the most traumatic in the history of the United States.
The 1980 eruption of Mount St. Helens is the most catastrophic eruption in the United States.
It began with a kind of landslide. The summit of a volcano collapsed and it decapitated itself, releasing the magma below, which gushed out in the form of fast-moving pyroclastic flows in a mixture of gas and ash. Then a column rose up into the stratosphere up to 27 kilometers high. In just a few minutes, this vertical column developed into a huge 25-kilometer wide mushroom cloud.
The winds coming in from the Pacific pushed the voluminous cloud of ash towards the east of the United States at a speed of 100 kilometers per hour. 11 states were affected by the ash, which even fell on Oklahoma, some 2,000 kilometers away.
It killed about 60 people, but it also destroyed hundreds of houses, hundreds of kilometers of roads, let's say infrastructure.
The eruption of Mount St. Helens is actually a huge revolution for the field of volcanology. It really changed our whole perspective on how volcanoes work.
It's a reference point. It happened in a technologically advanced country with lots of data.
That taught us also many lessons in terms of prevention, in terms of monitoring volcanoes, in terms of emergency crises. We always have something to learn from volcanic eruptions. So we build our knowledge on studying new eruptions.
Scientific studies around this previous eruption still serve as a solid working basis for volcanologists. But the explosion of gas and rock, the volcanic purge that occurred at St. Helens, pales in comparison to the volume that could potentially erupt from Yellowstone.
A few cubic kilometers were released, so compared to a super eruption, the ratio is something like 1 to 500 or 1 to 1,000.
Yellowstone volcano is about 2,500 times larger than Mount St. Helens.
Sometimes the imminence of eruptive events becomes clear within a few months, as in Mount St. Helens, but sometimes it's just a few days. That's the worrying aspect of the Yellowstone caldera. What if the time elapsing between eruptions is shorter than expected? It is a vital question in anticipating possible disasters because the Yellowstone caldera has the largest magma chamber on Earth.
If Yellowstone is reawaking now, how long is it going to take? How much time do we have before we need to take some sort of action? For this, we rely on crystals that are contained inside the magma.
It is vitally important to understand the warning signs of an imminent and massive eruption. The information locked in the crystals of Yellowstone's ancient lava flows provide clues about the conditions and processes that preceded the eruptions. Crystals are taken from the magma of the supereruption that occurred 2.2 million years ago, an eruption described as apocalyptic. If such an event were to be repeated in Yellowstone today, it would cover 2/3 of the United States in ash and kill millions of people within minutes. The explosive energy would be 22 times greater than that of the H-bomb. The objective of these analyses is to determine the time elapsing between the first signs of an eruption and the caldera exploding.
When magma cools, it generates crystals. Crystals are small particles inside the magma. So what we need to do, we go in the field, we collect a rock that is cooled magma that has been erupted.
And then we break them apart and look at the crystals and see, well, what did they record? And so essentially crystals can record all sorts of changes that happen within magma. So essentially they're like little recorders of the processes that are happening within the magma chamber.
This is important because it tells us something about how much magma was coming into the system before the eruption occurred.
Crystals ejected during a past supereruption allow scientists to establish the chronology of an explosion and define the time that elapsed between the fusion of magma in the chamber and its eruption. Using these direct witnesses to the cataclysm, scientists then attempt to predict the next awakening of Yellowstone.
The rock record is our best understanding of really what happened, especially for historic eruptions where we don't get to see them in real time.
It's a little bit like looking at what happened in the past to try to understand what will happen in the future. These sort of studies have been done for Yellowstone, and a part of the community speaks about reactivation times of months.
For now, measurements show that the caldera remains stable. But what happens when the pressure generated by the magma beneath the caldera reaches a critical point?
Magma is a thick liquid that forms at a depth of less than 100 kilometers. It then rises to a depth of less than 5 kilometers and forms a magma chamber.
We call a magma chamber that last stage of storage. That's the place where the magma was immediately before the eruption. At the moment under Yellowstone, the geophysical surveys suggest that there's something like 15,000 cubic kilometers of molten rock.
The top part of this chamber is probably around 4 kilometers at depth, and it can extend up to maybe 8 or 10.
It's what's providing all the heat, energy that's fueling the hydrothermal system.
Most of that magma chamber is actually solid. It's hot, but it's solid.
Typically, to get magma to mobilize and to move, it has to be at least 50% melt, and we're only at about 15 to 20% melt. That's not to say that there might be small pockets within there that have a higher percentage of melt, so that's kind of one thing that we're looking at, if we can get better resolution images of part of the magma reservoir. But right now we have kind of an overall kind of average over the whole thing.
Its presence just a few kilometers from the surface may be cause for concern. Scientists are closely monitoring any possible change in the state of the magma in the chamber. The more it liquefies, the more dangerous it becomes. The discovery of a new model of the interior of the magma chamber is precisely what now worries volcanologists.
The change from a quiescent state to an eruptive state implies the migration of magma from depth to the surface.
So for a long time, we have imagined a magma chamber, a volume filled with magma. This magma chamber, we conceive it as embedded in an elastic medium. So it's like blowing into a balloon that is inside a wood box. When you blow inside, you feel the pressure increasing. And we thought that the injection of magma was the parallel for blowing inside the balloon. The pressure would increase, and then the eruption occurred. As we see today at Yellowstone, we think that there are little pockets or smaller pockets of magma embedded in a system that is a bit like a sponge. When these systems are separated, the pressure inside is not sufficient to feed an eruption. Now, we think that if each of these pockets, the magma tends to go up, this may lead to these pockets getting connected. And if these pockets get connected, the pressure inside a connected system increases a lot.
The conclusions of this model of the magma chamber are crucial because these connections of magmatic pockets would generate zero or very few signs of seismicity. The magma would penetrate silently from one pocket to another, increasing the pressure before triggering a gigantic eruption.
We think that this process of connecting the various pockets could be itself the process that triggered the eruption. And I think one of the biggest questions is how big the next eruption will be in a sort of system like Jeloustoun.
While seismic activity may not be the most reliable clue preceding an eruption, others need to be studied closely. Geysers, pools, hot springs, boiling mud, fumaroles, all as spectacular as they are potentially dangerous, are in fact indicators of underground activity constantly being monitored by scientists.
We like to say that there's 10,000 thermal features in Yellowstone.
Yellowstone has half of the world's hydrothermal features, or geysers, in the world.
The best known in the caldera is the geyser known as Old Faithful. For more than a century, it has been spurting out eruptions more than 40 meters high every 90 minutes or so. It is the park's star attraction. These geothermal phenomena act as a thermometer for the rise in heat within the magma chamber. When the underground hot water source reaches 100 degrees Celsius, a gas bubble forms and expels the hot water in the form of a column tens of meters high. But if the temperature rises excessively, the geyser could change its cycle and sound the alarm. This is precisely what happened in the Norris Basin geyser area with Steamboat, the world's largest geyser. With unpredictable eruptions, it suddenly woke up in 2018 after 8 years of inactivity, triggering a 120-meter-high column of water.
These volcanoes are active, they always do something. They always inflate, deflate, they emit gas, they have earthquakes continuously. So one of the bigger problems is to understand at which time do we have to start worrying.
One striking feature of the landscape around the Yellowstone hydrothermal system is the forests of dead trees, collateral victims of degassing and real sources of danger. Grand Prismatic is the largest hot spring in America. The size of a football field and as deep as a 10-story building, the pool is composed of sulfur and iron dioxide, and its temperature rises to 70 degrees Celsius. The hydrothermal explosions associated with these basins, caused by underground water suddenly turning into steam, represent a threat. When water transforms, it expands rapidly, creating a very large volume that needs to escape. If the steam remains confined, it explodes.
These sorts of hydrothermal explosions could happen just about anywhere that there's hot water moving around beneath the surface. In fact, in 2018, there was a small pool called Ear Spring, and it suddenly started erupting as a geyser. It hadn't done that since, I think, at least the 1950s. Why did that happen in 2018? We don't know the answer to that, and that's something that we're really trying to focus on, to understand these small changes.
Ground movement, earthquakes, the arrival of magmatic gas, those are really the three components, or the three factors that we will rely on most for deciding whether or not eruption is likely.
The unpredictable and uncontrollable nature of these gigantic volcanic systems is a source of great anxiety for scientists. Seismic alerts and geothermal thrusts are not enough to flag a catastrophic eruption. The intervals between explosions need to be closely examined too. The past 3 super eruptions at Yellowstone suggest that the rate of recurrence is approximately once every 700,000 years. So are we dangerously close to the end of a cycle?
There seems to be periodicity, but a statistic based on just 3 eruptions has no real value. What we can say, though, is that a super eruption is possible sometime in the millennia to come, or within the next 300,000 years.
The cycle nature of these systems is so challenging, because I think in every system where you have these periods where you have more volcanism and then less volcanism, you're always trying to figure out, are you at the end of a cycle, at the beginning of a new cycle? Like, where are you in the cycle?
It's entirely possible that we're not only at the end of the current cycle of Yellowstone activity, but there may not be that much in the future. That's a possibility. Unfortunately, I suppose, we won't ever be able to answer that question because we're never going to see it.
The caldera's huge dimensions, plus the danger lurking within Yellowstone's active magma chamber, allied to the resurgence of earthquakes beneath the park, are all alarming indicators. The real question being asked by scientists around the world is not whether or not the eruption will take place, but what the nature of the event will be when it does. As with many alarming possibilities, scientists may be unable to provide an accurate timeline, but they can imagine the potential consequences of an eruption. But will they be able to give the alert in time? The prospect is undoubtedly a frightening one. A super eruption at Yellowstone would quite simply be a geological event that disrupts social organization throughout the Northern Hemisphere, and in the worst-case scenario, wipe out the entire human race. The major danger of this type of explosive eruption is the phenomenal amount of energy expelled by the volcano as it purges itself. The most important factor is the volume emitted. 1 cubic kilometer of magma ejected during a regular eruption would bury the entire Paris region beneath its ashes. In the case of Yellowstone, we are talking about 1,000 cubic kilometers of magma, or 1,000 times more energy.
It's all about scale. As I tell my students, an eruption of 1 cubic kilometer already has a huge impact. Increase that 100-fold, 1,000-fold, up to 1,000 or even 10,000 cubic kilometers, and the event becomes absolutely catastrophic.
The energy that the Yellowstone caldera could potentially generate in the event of an explosion is simply unimaginable. Predictive models show that a super eruption at Yellowstone would be of unprecedented violence.
It starts with a normal eruption, shooting a plume of ash and fragments into the air. Then, as the eruptive conduit widens, so the magnetic flow increases. And all of a sudden, the magma projections increase dramatically, and you have what are called ignimbrites, coming from the Latin word meaning fire rain.
These eruptions expel clouds of gas and fragments of broken up magma. Some of these clouds and fragments, they spread out over the ground, and they can travel at hurricane speeds up to, well, tens of kilometers away from the volcano.
It's actually a burning cloud of ash, gas, and fragments traveling at 600 kilometers an hour at temperatures of 600 to 700 degrees, hot enough to immediately fuse into rocks. The curls of ash unleashed with lightning in the plumes are like the wrath of the gods, the fury of Zeus or Jupiter.
And the super eruption could cover several thousand square kilometers.
And because the pressure decreases in the reservoir, it becomes a sort of vacuum cleaner that is sucking new magma coming in. And if this process is keep going, eventually a caldera collapse can start. And when the roof of the caldera pushes on the reservoir, it makes the magma come out from the fractures around the caldera. And then these especially produce pyroclastic flows.
Gigantic, extremely high-temperature fiery clouds composed of ash, gas, and rocks roll down the slopes of a volcano, seeping into the surrounding terrain, petrifying the landscape.
Pyroclastic flows destroy everything that is on their way. They can reach 500, 600 degrees centigrade.
For sure, pyroclastic flows would be the most devastating phenomenon associated with a super eruption. Basically, there's no escape from pyroclastic flows.
Life on the ground, then, would be sacrificed. But there is no escape in the skies above either. Without evacuation, the explosion would instantly kill any sentient being within 1,600 kilometers around the caldera, as it expels 1,000 billion tons of matter into the atmosphere. Then, a few days after the explosion, comes the most formidable enemy of all, volcanic ash.
Volcanic ash is glass. It's like if you take your window glass, you break it with a hammer, you make a little powder, and then you throw it into the atmosphere. Previous eruption of Yellowstone have covered in ash essentially the entire North American region.
In the immediate vicinity around Yellowstone, for instance, we're supposed to get over a meter of ash, and that goes all the way down to Salt Lake City, over to Billings, Montana. It's a huge extent of a meter of ash, which is a crazy amount of material.
But most of the death associated with the volcanic ash is related to the collapse of buildings. Because you can accumulate a lot of ash on the roof of a building that can collapse.
In addition to destroying cities, the ash mantle contains still glowing residues of magma, causing forest fires and destroying crops and herds as it falls to the ground. The ecosystem necessary for human life is swept away. Wildlife is threatened. North America would then be plunged into darkness. No more electricity, no more drinking water. Particles of volcanic gases then escape. As they reach the stratosphere, they threaten the entire planet.
These gases are liberated into the atmosphere, and sulfur, for example, can produce aerosols in the atmosphere.
These sprays filter the sun's rays, meaning fewer solar rays reach the surface of the Earth. They form an opaque veil, triggering cooling on the ground of anything from a few tenths of a degree to a few degrees in the case of the very strong eruptions.
This is what generates volcanic winters.
A volcanic winter is a significant drop in temperature following a major eruption, a super eruption, which radically disrupts the climate.
Modeling suggests that a super eruption could cause cooling of several degrees centigrade, and certainly enough to disrupt growing seasons for several years. And that, in turn, can lead to global famine. So this is the real perhaps the even greater problem about super eruption.
It's chaos, a major ecological and human disaster.
Far from fantasy, volcanology researchers are constantly studying every eruptive event on the planet in an attempt to anticipate any looming crisis at Yellowstone. The study of previous explosions can help produce predictive models. But the problem with Yellowstone is the scale. Compared to the eruptions in Iceland or the Philippines, the effects would be 1,000 times worse.
There was a famous eruption in Iceland in the spring of 2010 when the Eyjafjallajökull volcano erupted.
It was a moderate eruption, had a volcanic explosivity index of 3.
Then in April, the magma migrated to another place, beneath a glacier. From that moment on, everything changed.
The hot lava coming into contact with the frozen glacier caused a huge plume of steam to rise 10 kilometers into the atmosphere. At the same time, an anticyclone in the north of Iceland pushed the plume right across Europe. European airspaces were closed down, costing billions of euros in just a few days. Iceland isolated itself. This major eruption went on for 2 weeks, with no deaths or injuries. But this ordinary event, coupled with unfavorable winds, showed the fragility of our society.
Eyjafjallajökull demonstrated how vulnerable we are, even to small eruption.
Compared to a super eruption in the Yellowstone, what happened in Iceland in 2010 is a ratio of 1 to 1,000.
So if VA7 had to happen now, in the world as we have it now, the impact would be devastating.
What's in store for Yellowstone and the surrounding area is far worse. The Icelandic eruption was not from a supervolcano and had no impact on the climate. The same was true of the dramatic eruption at Pinatubo in the Philippines, the most significant disaster of the 20th century.
So if we want to have sort of some idea of what might happen after a super eruption, we could think, what were the consequences of one of the biggest explosive eruptions of the 20th century? And by that I mean the eruption of Pinatubo in 1991.
The terrible rumbling from Mount Pinatubo has been going on for 6 days now. A new 3-kilometer-long crack has appeared on the southern slope. In late 1991, having been dormant for 500 years, the Mount Pinatubo volcano exploded. The consequences were catastrophic and affected the entire planet.
The explosions sent fine particles of magma ash and sulfur-rich gases into the stratosphere.
All life was wiped out in a 14-kilometer radius around Mount Pinatubo. Collapsed roofs claimed many victims. 300,000 people were evacuated, and nearly 900 people died. Infrastructures broke down, and looting became commonplace. Nearby villages suffered mudslides for many years afterwards. The surrounding soils became contaminated. It was a gigantic human and ecological disaster.
And it did lead to cooling at a global scale of a fraction of a degree centigrade over the following few years. So this gives us an idea that such a small eruption can have an impact on climates.
Luminosity was reduced by 10% across the surface of the Earth, a colossal figure. The ash circulated around the globe for 3 whole years, resulting in torrential rains and unusual flooding in the United States. The subsequent hole created in the ozone layer took 30 years to fill.
This erupted a few cubic kilometers of magma, so already several hundred times, if not 1,000 times smaller than a super eruption.
So for eruption like the size of Jeloustoun, this could have an impact and generate few years of volcanic winters, at least what we think.
Learning from previous disasters is one way for volcanologists to anticipate and better prepare populations in the event of an eruption. But some visionary scientists are playing the sorcerer's apprentice and trying to find other preemptive solutions. NASA, for example, decided to take things further. After the eruption at Mount Pinatubo in 1991, they began working on a plan of action that could be rapidly implemented. Given that a volcanic eruption is a way of purging the pressure that builds up in the magma reservoir, the engineers' idea was to schedule regular mini-purges.
Let's just take it seriously for a minute. Okay, so the idea would be, is it possible, for example, to put drill a hole down towards the magma body and maybe allow gases to escape gently so you reduce the pressure and prevent the molten rock, in fact, eventually coming to the surface? That really is still in the realms of science fiction, I'm afraid.
The NASA study to drill the volcano and cool it down was not realistic. It was basically a calculation. It was sort of the thing you do on the back of a napkin in a bar.
And this will take tens of thousands of years, and even with the risk of generating phreatic eruption.
But it didn't account for the fact that there's always more heat coming in.
Once you start to trigger the formation of gases, there is a risk that it's a self-feeding process. And once you start it, you won't just control the creation, the release of gas, which then increases the pressure, which then leads to an eruption.
Jeloustoun is already water-cooled. This is why there is a geyser system that is continuously releasing heat from this system.
We can't even essentially make a lava flow go into a different direction many times. There's no way we're going to stop a super eruption from going if it wants to go.
There's no way of preventing it. You just got to kind of prepare for it.
So our scientific responsibility is to mitigate the impact, not to change nature.
Our responsibility is to avoid that this natural phenomena becomes an impact on the population.
We just have to monitor it, understand the system, how it works, what we might expect to see in terms of hazards, and then essentially make a response plan based on that information.
Volcanologists around the world collaborate with each other. Depending on their various areas of research and expertise, they pool their work to better understand what is happening at the center of the Earth. The challenge for crisis cells all over the world is to ensure the earliest possible evacuation of populations around volcanic areas.
There are more than 800 million people living around 10 kilometers of an active volcano, so it's a big part of the global population, so we need to take care about this.
A volcano goes through cycles. Sometimes we can think that a volcano is extinct because it hasn't shown any sign for many years. People get used to it and can start also building houses close to volcanoes. And then all of a sudden, a volcano can reawake after hundreds of years. And this is why this type of volcanoes can be particularly dangerous for people.
The most worrying and the most boring result for a volcanologist is a non-eruption. It's already happened. All the signs are red, an eruption seems imminent, the area is evacuated, and nothing happens.
There are an awful lot of examples of volcanic crises where populations were evacuated and nothing happened, and then the population tends to lose trust in the scientists.
If they lose the trust, this could be very dangerous, because perhaps then something happened 2 years after, when everybody is back.
We volcanologists are spectators. We try to understand what the volcano decides.
Volcanologists know that the only solution is increased monitoring of volcanic systems, such as Jeloustoun. In 2015, researchers from the University of Utah made a discovery as spectacular as it was unexpected when they located a gigantic, undetected magmatic reservoir.
The Jeloustoun plumbing system, it was not limited to the very large 10,000 cubic kilometer reservoir that is somewhere in the upper crust in the first 10 kilometers. But there was a much deeper reservoir where about 46,000 cubic kilometers of magma are stored.
Lying beneath the already known magma chamber at a depth of some 45 kilometers, this reservoir is an alarming discovery. 19 kilometers high, 64 kilometers long, and 40 kilometers wide, it contains 46,000 cubic kilometers of magma, enough to bury an area the size of Texas beneath 15 meters of material. It is currently the largest magma chamber on Earth.
That's a place where magma can reside for much, much greater intervals of time, much longer than for a single eruption. So that's really the reservoir that can last the lifetime of the volcano.
While the rocks are not completely melted, most are in a solid, spongy state, and they are extremely hot, with pockets of liquid. Scientists have calculated that on average, 9% of the magma in the known chamber is molten, with a further 2% in this new reservoir below.
From this place, there are little volumes of magma that keep the system that is in the last 10 kilometers alive.
And it is possible at some point that it might inject some of that lower viscosity magma into the upper magma chamber. That may be the kind of thing that would cause a rejuvenation. It might be able to melt some of that stagnant upper magma chamber.
So the thing that this shows us is that even if Jeloustoun is not erupting now, it's an active system.
The discovery of this reservoir helps explain why the carbon dioxide emitted by Yellowstone's soil and geothermal springs exceeds the volume that the only known chamber could be expected to produce. Scientists now have a better understanding of the complexity of the Yellowstone magmatic system.
Yellowstone is definitely a big system. It is really massive, not only in terms of its aerial extent, right? The caldera is huge, it's tens of kilometers across, but also in terms of its depth. And the evidence for that is all around us, not only in the geysers and the hot springs, but in all of the volcanic rocks we see, not just here, but trending all the way across southern Idaho. This has been a long-lived and very large volcanic system.
On a human timescale, the eruption of the Yellowstone caldera remains a very rare occurrence. The risk is comparable with that of the Earth colliding with a meteorite. The super-eruption fantasy is part of an irrational fear particular to the human race, the only species aware of its own death.
You don't necessarily live in fear from these things, because what can you do about it, right? It's just part of the way the Earth works.
The Earth is neither nice or nasty. The same is true of volcanoes. Humans are, of course, dependent on nature.
So you can plan on it, you can model, you can prepare, and you can gain knowledge on the system so we can better disseminate that knowledge to people who live in the area and be well prepared for certain events.
If NASA's purge technique or some other as yet unknown solution fails to work, it is likely that a supervolcano such as Yellowstone will one day wake up and trigger a mega explosion and global cataclysm.
The worst possible consequences of a supereruption might actually get close to those that we might imagine Hollywood would come up with. And that would be an existential threat to human beings, mainly because of continued famine. So there have been ideas that it could lead to the end of our species, but that really is an extreme case. It will certainly end up with a complete change in our civilization, that is for sure.
I'm optimist in this case. I don't think a super eruption will cancel us from... I think we are much more capable to do that by ourselves than an eruption, but obviously will have an impact.
While the Yellowstone supervolcano is one of the most beautiful representations of nature, it is perhaps also its most remarkable paradox. The raw beauty of the landscapes, the geothermal diversity, and the purity of its colors conceal a frightening reality. Here, many kilometers below one of the Earth's rarest and best preserved ecosystems, lurks a volcanic complex which, should it ever erupt, would completely reshuffle the cards of human activity.
We're making progress in forecasting when an eruption will occur, but we're a long way behind in forecasting how it will occur and how big it will be.
These are the big questions we ask ourselves for any volcano on Earth.
In Jeloustoun, the paradise visible on the surface exists alongside and above the hell down below. This unique system, forged by fire and water over many millions of years, allows researchers to observe, study, and understand the evolution of our planet.
The scientific opportunities here are amazing. And the lessons we learn at Jeloustoun, even if it's not going to erupt, we can apply to other caldera systems around the world.
There's always something new. It's such a dynamic place. It's always changing. Every year something happens, all of it integrated together gives us a better idea of how the Earth works.
The long history of the universe is littered with examples of physical phenomena such as extinction, climate change, cosmic collisions, and dead planets. The disasters of the past are etched into our DNA and maybe, as some believe, in a collective ancestral memory.
Any eruption teaches us that we are very small in front of nature. So we think that we are in control, but we are not in control. We can study as much as we can, but at the end, we need to study to be able to respect nature, not to control it.
So this is why we should take care and use super eruption as a demonstration of the supreme power of nature. We are nothing in comparison to that. So we should have a little bit more respect for nature than what we do now.